Hi, welcome back to Math 112. We're going to go ahead and dive right in. Now, vectors are a way by which we can describe movement in space. So vectors have got both a length and a direction. So let's start by just talking about a couple of points in space. So let's say we want to go from this point, which is the point -3, 1, and consider this point over here, which is the point 1, 2, 3, 4, 1, 2. Yeah, let's not do that one. Let's do this one, 4, 3. Okay. Now we know how to do some things with these 2 points. We can find the point that is halfway in between them. We can find the distance between them. And what we're going to talk about now is a way that we can describe the movement from one point to another. So let's say this is the point A, this is the point B. What I've just drawn is the vector AB. Now, the vector AB means we move from point A to point B. And we can talk about how we can do this in a couple of different ways. Probably the most intuitive way to do this is in what we call component form. So when we define vectors, we need to talk about how far we're moving and in what direction. So generally we have got 2 standard vectors. We've got a vector we call I, which is just a movement 1 unit in the horizontal. And so one way we can describe I is by talking about what we mean as its or what we call the displacement or the component form. So think about an ordered pair, but instead of coordinates, we're going to put in displacements. So the vector I, we move 1 unit horizontally and 0 units vertically. This is I. Now here's the thing about vectors. That can be I there at the origin. This can be I here because, and I could be out here, because vectors describe displacement. So they can be placed anywhere in the plane and still mean the same thing. Okay. Now we have another standard vector that we call J. And the standard vector J is just a unit vector, a vector of length 1 that moves vertically. And J then is 0, 1. All right, so let's go back to our AB vector. Think about what we did. We moved 1, 2, 3, 4, 5, 6, 7 units horizontally and 1, 2 units vertically. So this is one way of expressing the vector AB. It's called component form. And in component form, we describe the horizontal displacement and we describe the vertical displacement. Now, we can also write this vector in terms of I and J. So when I did this little notation here, I wrote my vector I 7 times. So we can also write vector AB as 7I plus 3J. And those are vectors, so we put little directional arrows over them. This is also a component form. Okay. Now, generally, when MyOpen Math asks for component form, they want this as component form. On the exam, I'll take either one. Usually, this is called. So yeah, usually this is called component form. It kind of depends on the world in which you're living. And when you're doing engineering calculations, I tend to see this form more frequently. When you're doing mathematical calculations, we tend to use this form. Okay. So that is, so a couple more things here. So AB, if we go from A to B, we go +7 in the horizontal direction, +3 in the vertical direction. If we want to go to vector BA, well, that's different, right? Because going from B to A, we actually go left 7 and down 2. My bad. This should be a 2. Right? Or we could write BA as -7I minus 2J. So as I said, direction matters. All right, so what else can we do? Well, there's another way to describe a vector. And we can also use an angle and a distance. So the distance between the 2 points is called the magnitude of the vector. So the magnitude of AB is the distance between the point A and the point B. So that's going to be -3 minus -4 squared plus 1 minus 3 squared, which is the square root of 49 plus 4, which is the square root of 53. So we can also, so we now know the magnitude. This is the magnitude of my vector. Now, if I could find that angle theta, then I would have a way of describing my vector in terms of a distance and an angle. And we can do that because we know that the tangent of theta is y, the y displacement divided by the x displacement. So theta is the inverse tangent of vertical displacement divided by horizontal displacement, which is, if we bring up Desmos, and we're going to do this work primarily in degrees, inverse tangent of 2/7, 15.95 degrees. So we can also describe AB as the square root of 53 at 15.95 degrees. Now, I usually add a little directional arrow, but you can also say 15.95 degrees from horizontal. Okay. So you've kind of got the basics of vector notation and what a vector means. We're going to come back in the next video and we're going to talk about what it means to add two vectors together. But before we do that, let's talk about going backwards. So suppose you are given a vector with length 7 at 135 degrees. Now, if it doesn't say anything else, we presume that that angle is in standard form. In other words, what we're looking at is this guy. Well, not that guy. This guy. That is 7 units long at an angle of 135 degrees. Now, what we want to do is find the component form. One way to think of the component form is to think about this point out here and how far over we would go horizontally to get to that point, and how far vertically we would go to get to that point. Now, if we envision that there is an imaginary circle out here of radius 7, we know that the x-coordinate of this point, because that is what this horizontal displacement is the x-coordinate, and the y-coordinate is the vertical displacement from the origin, right? So, no matter where we are in space, the horizontal component of a vector is always equal to the magnitude times the cosine of the angle that vector makes with the horizontal. Now, I'm going to use the 135 degrees because I'm given the standard vector. But we could also use this little guy in here, which is 45 degrees. And we can do that and just remember to take into account the directionality. So no matter how we do it, we end up with an horizontal displacement of negative 7 times the square root of 2 over 2. And a vertical displacement of positive 7 square root 2 over 2. So in general, so that is the x and y components of this vector. So my vector can be written as, in component form, negative 7 square root 2 over 2, comma 7 square root 2 over 2. So in general, if a vector v has got a magnitude, so for any vector v at some angle theta, with the horizontal, so that can be either an internal or an external angle, just needs to be relative to the horizontal axis, then the x component is equal to the magnitude of that vector times the cosine of that angle, and the y component is equal to the magnitude of that vector times the sine of that angle, and that comes direct from right triangle trigonometry. All right, so now that we've got component form, let's talk about what it means to add two vectors together.